Okay, now that we have derived the method of least squares estimators, so beta naught hat was y bar minus beta 1 times x bar, and beta 1 we had derived to be sxy divided by sxx. We can carry out various proofs on these estimators. The first one is that whether they are unbiased estimators or not. So if we recall from our earlier discussions, an estimator is an unbiased estimator if over repeated sampling its expected value is equal to the true value. So expected value, using this generic notation theta for parameters, if the expected value of theta hat is exactly equal to the true parameter theta, then this estimator is called an unbiased estimator. And using the fact that any given observation yi can be written as beta naught plus beta 1 times xi plus epsilon I, and y bar, we can then write the average in terms of the average of x and the average of noise, which essentially is 0. It is possible to show that these estimators, beta naught hat and beta 1 hat, the method of least squares estimators, are unbiased estimators. Now this proof is for you to derive. I'll give you a small hint. So all you have to do is to prove that the expected value of beta naught hat is equal to beta naught, the true parameter, and expected value of beta 1 hat is equal to the true parameter beta 1. In order to prove this, you have to first express beta 1 hat in terms of the true parameter beta 1 plus summation of xi minus x bar times epsilon I divided by xi minus x bar whole square. So this is the hint. If you can express beta 1 in this form, then it'll be easier for you to prove that the expected value is equal to the true value beta 1. And this essentially, this expression comes after a little bit of algebra using the expression of beta 1 hat from here. Right, so far we have discussed about the regression coefficient beta 1 and beta naught. But what about sigma square? That's also a parameter of this model, right? The variance of the conditional distribution of y given x. So sigma square is essentially the variance of y given x. And we can write an expression for variance. So what should be a natural estimator for sigma square? Just the variance of y given x. So if you recall from our definition of any variance, variance of any variable z is given by summation zi minus z bar whole square divided by n. If I write it as n, it would be a natural estimator, and we also know that the mean of any random variable z is nothing but summation of zi divided by n, right? So in case of mean, we divide by the denominator is the total sample size n. We can do the same thing. That's the more natural thing to do. So that's why this is called a natural estimator of the variance. However, if you recall from all the textbook, the school standard definition of standard deviation and variance, we know that it's often written as n minus 1 instead of n. And why is that? Isn't using n the most natural thing to do? Because that's what we have done for the mean. However, in case of variance, it turns out that if you use n in the denominator, the estimator will not be unbiased. Since we want our estimator to be unbiased, we use n minus 1 in the denominator. This n minus 1 comes from a concept in statistics called degrees of freedom. I leave it to you to read a little more details about it, but I'll give you an intuitive interpretation. See, what is happening in case of mean is that we are using all the sample values that are observed, zi's, z1, z2, z3, etc. to zn, right? However, in case of variance, when it comes to calculating the variance, we are not only using the observed values zi's, but we are also using this term here, which is the z bar term, right? Now this z bar itself is an estimate, which is the mean, the z bar. This z bar, since this is also estimated from the sample, there's a level of estimation. So when you are calculating variance, you have already taken, you are depending on this estimated value of z bar. Because it is only one parameter, one estimator z bar that we are using, we are subtracting minus 1. If instead of one parameter we had used two parameters, which are again estimated from the very sample, in order to get the third parameter, then we might use a degree of freedom, which is n minus 2, right? So with this little background, let us come back to our parameter sigma square, which is there in the simple linear regression model. And sigma square we know is the variance of y given x. We have proved that this is also the variance of the error terms, right? So the variance of y is nothing but y bar, yi minus y bar whole square summed up over all the observed values. And we know that y bar, the expected value of y given x, is nothing but mu y given x. This is the y bar. And because I am indexing over I write mu y given x equal to xi. And this I am summing up over all the values. A natural estimator again would be to divide by n. However, this is not an unbiased estimator. So this is not unbiased. In order to make it unbiased, the denominator has to be subtracted. But by what amount shall we subtract? Should it be n minus 1 or n minus 2 or n minus 3 or what? Now note here that in this expression, this mu y given x, what is this? We are now going to write it as beta naught hat plus beta 1 hat times xi. So mu y given x equal to xi will now be written in this form, right? So now it's not just one parameter but two parameters, this beta naught and beta 1. There are two estimators that we are going to be using to plug in to this expression to get sigma hat square. So therefore my degree of freedom, the denominator, will be reduced by 2. It will be n minus 2 in the denominator. And this is what is given here. So you see an n minus 2 in the denominator. Again, there is a little more trick that we have applied, which is mu y given x equal to xi. Again, this is nothing but yi hat, right? The predicted value from the simple linear regression model. This we can write here, yi minus yi hat square. And from our definition of the error term, the L function, this is nothing but the RSS. So the numerator is RSS, the denominator is what is called the error degrees of freedom, EDOF. Okay, so now we have the method of least squares point estimates for all the parameters, beta naught hat, beta 1 hat and sigma square hat. However, in our discussion on testimation, we had stressed again and again that it's not just the point estimates that will be reported. You must always accompany them with their standard errors. Those standard errors will be used to compute the confidence intervals or to carry out any hypothesis testing on these parameters. Alright, so now we'll see how to get the standard errors in these parameters. Again, using these two expressions, we had seen this earlier. You can express beta 1 hat as beta 1 plus xi minus x bar epsilon I summed up over all the i's, and xi minus x bar whole square summed up over all the i's. If you use this form, then you can get the expressions for the variances of beta naught hat and beta 1 hat. And the square root of those variances would be the standard errors. Again, recall, why is it that these estimators beta naught hat and beta 1 hat are uncertain? They are uncertain because you are fitting a particular model between x and y, a simple linear regression model, based on a particular given sample. If you had taken another sample, then you would have gotten a different value of beta naught hat and beta 1 hat. So in the sales versus advertisement, let's say I took data of 50 years in Mumbai to get a relationship between advertisement and sales. If I had another sample of 50 years in Kolkata, I would fit another straight line, another simple linear regression model, and I'd get another value of beta naught hat and beta 1 hat. So this variability over repeated sampling is called sampling variability, and this is why there will be errors in these estimators beta naught hat and beta 1 hat. Right? So we can compute their variances, and once we have the variances, we can take their square roots to get the standard errors. So I leave it for you. This is for you to derive. It's fairly straightforward. After you have used this expression, you get the variances and take the square roots. So this is what you will eventually get as the standard errors. And it's usually the standard errors of beta naught hat and beta 1 hat that we are more interested in, because we do hypothesis testing only in these two parameters. So although sigma square is in fact by definition a parameter of the simple linear regression model, but we never really do any kind of hypothesis testing on it. Its value is used in calculating, like for example, you will see a sigma square term here and a sigma square term here. But it's not really a parameter that is used for hypothesis testing. Its confidence interval is not of much consequence. Whereas beta naught hat and beta 1 hat are the two estimators where, in fact, more important out of them, and this we had discussed earlier, is beta 1 hat, because this is the parameter which will tell us what sort of a linear dependence is there between x and y. Right? So using these standard errors, we can find out the confidence intervals of beta naught hat and beta 1 hat, and we can also do hypothesis testing on them.